Okay, is that mic on? Can people hear me? Great. Okay, welcome to this talk. It's a talk on cryptography, it's sort of listed up there. It's quite a theory-heavy talk, but I've got some sort of PHP examples towards the end that sort of show you how you might use it if you actually want to encrypt things in your own applications. So, a quick introduction. What is cryptography? Well, what we're sort of looking to cover in modern cryptography are sort of three important areas. The first one is message privacy. That's probably the most obvious one. That's ensuring that any communications that you send can only be read by the person you sent it to, the person you want to be able to read it. Another thing that you need to be able to do is verify messages that you've been received. So make sure that it's the message that was actually sent to you and not sent by someone else or sort of tampered with on the way. And a sort of final concern that we sort of look at with cryptography is identity verification. So making sure that it is actually the person who you thought was sending you the message who actually sent it. First of all, if you've ever been into any talks on application security and things, it might have included a slide that looks a bit like that. During this talk, I'm going to take you on a brief journey through the evolution of modern cryptography and show you exactly why it's quite so hard to sort of just invent your own cryptography algorithms and things like that. I'm going to be starting with some of the old historic ciphers, which are really easy to understand and have a look at. And then we're going to have a look at some of the inner workings of some of the ciphers we actually use today. So, first off, with some of the historic ciphers. The Caesar shift. Probably all heard of this one. It's probably the simplest cipher you can think of. In order to encrypt a message, you're looking at translating the alphabet. Just up the letters by one, or two, or something. On the slide here, I've got an example where you transition by moving the letters up by 3. So in this, if you want to encrypt the letter A, it becomes a D, B becomes an E, and so on and so forth. Now, this would be a very short talk if this cipher was actually any good. So what's actually wrong with this as an algorithm for encrypting things? Well, for any given sort of alphabet, be it the English alphabet or say Japanese or something like that, there's only a very small number of possible keys that you can use with this cipher. Even if you go to like the full range of ASCII characters, there's only 255 different possible keys. So any attacker that wants to read a message that you've encrypted with a Caesar shift need only sit there for a few minutes and try every single possible key until they get a message out that makes sense. This is helpful in illustrating one of the first important aspects of a strong cipher in the fact that it has to have a lot of keys. Because it's no good if your encryption cipher has so few possible keys that anyone who wants to read the message can just try them all until they're successful. So one attempt to sort of improve upon this, I suppose, would be the substitution cipher. A substitution cipher is implemented by swapping each of the letters in the ciphertext for a completely different letter. So you're not limited to just the next one up the alphabet, but you can have a completely random permutation. So as you've got on the slide here, the letter B there, moving to N, C to Q, etc. And you can have sort of any permutation of the alphabet that you fancy. It's significantly better in the number of keys. In fact, there are 403 septillion, 291 sextillion, 461 quintillion, 126 quadrillion, 605 trillion, 635 billion, 584 million different possible keys for a substitution cipher. So given that we've got so many different possible keys, why aren't banks actually using it to secure your credit card details and things like that? Well, one of the weaknesses of the substitution cipher is sort of the biggest nemesis that cryptographic algorithms face, and that's statistics. Although the number of keys is equivalent to about an 88-bit key, which isn't as strong as some of the ciphers we'll look at later on, which use 128 or 256-bit keys, it is still just sort of like on the edge of what we would be able to brute force the computer. But unfortunately, due to the simplicity of the cipher, it fails to hide the underlying patterns in the data that you've encrypted. And so if we want to actually recover the original plaintext which was encrypted, we just need to look at patterns in the ciphertext. Here's a graph of the relative frequency of characters in English text. You can do the same for French or German or any other language that you fancy. And you'll sort of see that the most common characters in English are E and T and A. And even if you encrypt a piece of English text with a substitution cipher, you'll still find that the most common characters are there. So you can have a look at what the most common character in your ciphertext is, and you can sort of make a bit of a guess that that's probably an E, if you know it's English text. And then the next most common one is probably a T. From there, you might be able to work out words like the, then, and things like that, which are quite common words, and start to pull out a picture of what the key looks like and eventually work your way through and decipher the text. You may well have already done this yourself as sort of a bit of exercise. So the next cipher we're going to look at attempts to sort of improve upon this problem and try and hide those underlying patterns in the data. It's called the Vigenère cipher, and I have probably pronounced that completely wrong, I'm sorry. It's one of a class of ciphers called polyalphabetic ciphers. They're so called because they use multiple different alphabets to encode the text that you're sort of encrypting. This makes them far, far stronger against the letter frequency analysis that I just showed on the previous slide, and sort of starts to hide the patterns. So how this cipher looks is, the first step, you would pick a key phrase. So in this example, I've picked the word key, nice and simple. The code word is then used to determine the encoding of each letter in your message. How we do this is, if you remember back the ceasar shift, a few slides back, and how we shifted up each letter by a fixed amount, well, we do exactly the same for this cipher, except for instead of shifting the entire message by a set number, we use different shifts depending on the current letter of the code word that we're using. So as you can see, for the first letter of our message, we'd use the first letter of the keyword, which is K, and shift so that A equals K, B equals L, etc. For the next letter in the cipher, it's an E, so we use the ceasar shift where A maps to E, and so on and so forth for every letter in your code word. Obviously, you'd probably want to pick a longer word than key. How you'd encrypt a message with this? We've got maybe a sample message that we might not want anybody reading. And we start by using each letter in the key to encrypt it. And once we run out of letters, we go back to the start and repeat. So that's what we get out with. Is this cipher secure? Still, unfortunately, not really. It did last for a lot longer than some of the other ones. It took a while before someone figured out how to break it. History actually credits Charles Babbage with the method to break it. However, it wasn't until 1985 that this was recognized. Until then, Frederick Kazicki had been credited with the discovery, as he was the first one to go public with it, effectively. And it's him that the technique is named after. Obviously, unlike the substitution cipher, we can't actually use frequency analysis to break this, as each letter has multiple different encodings. If you were to do a frequency analysis, you'd hopefully get a roughly flat graph where every letter is roughly equally used. So you wouldn't get much meaningful insight into how the cipher has been encoded. But what we can do instead is we can have a look at repeated sequences in our ciphertext. So here you see the letters DLC have been repeated twice in the ciphertext, and they represent the words "the" in the original plain text. And you can see that we've got like a gap between these repetitions of 12. Now, what these repeated sequences often represent is common words that were in the plain text. And by having a look at how far apart in the ciphertext they appear, we can make a guess as to what the length of the keyword might be. So in order for them to appear 12 apart, the keyword's got to be a multiple of 12's got to be a multiple of the length of the keyword. So that leaves us with 2, 3, 4, 6, or 12 as possible lengths. Obviously, with a longer message, we'd see more repeat sequences, and that would help us narrow down what the length of that key is. What you can then do, once you've had a guess, I mean, I didn't make a guess because I already knew, you can take every nth character of the ciphertext and break it into separate groups of letters. And then you can actually just do frequency analysis on that subset. And that will give you an idea of which ceasar shift is being used to encrypt that particular subset of letters. Once you've done that, you can sort of unscramble it and apply that shift back, and you effectively recover the key and can decrypt that text. I have actually produced a little bit of a challenge if anybody's interested in having a go. It's a slightly more complicated Vigenère cipher, which you can sort of use that technique to have a go at. I'll put the link up again at the end if anybody's interested in having a crack at that. It was about another 100 years before the next sort of notable cipher was brought into use. World War II saw many attempts to mechanize cryptography. So instead of using paper and pen, people would actually use machines to do their encryption. The most famous attempt at this was the Germans' Enigma machine. And although all the sort of like the major powers in the war were using variants on this sort of technique. So this is an Enigma machine. It consists of several parts. There's a keyboard in the middle. That's used to type out your message. Then there are a set of rotors at the back here. They're part of the encryption mechanism. They're an electrical circuit, effectively. Then you've got this lamp board in the middle. That tells you what the actual encrypted or decrypted letter is. So you can write that down off the thing. And then finally, there's a plug board at the front here, which was used to provide further sort of obfuscation of the message and sort of swapped different letter pairs. Now, up to 13 swaps were possible, but generally only 10 of those were actually used in one go. Having a bit of a look at how the rotors work. To encrypt a letter, you sort of press the letter on the keyboard, and that sends an electrical signal through the Enigma machine, through each one of the rotors, which sort of scrambles it like this. You can sort of follow the path. Through a reflector at the back, which was basically just a sequence of hard-coded wires that reflected it back. And then all the way back through the rotors once more, in order to light up a letter on the lamp board. Once you press that key, it would also mechanically rotate one of the rotors by 1 point. That would mean that when you came to press the same letter again, it would take a completely different path through the rotors, and therefore light up a completely different letter on the start. Obviously, each time you press the letter, it rotates a rotor. Once a rotor has completed a complete rotation, it also rotates the next one in sequence. And as such, you're sort of rotating the whole set before you come round to a repetition. Now, Enigma is a really famous cipher, but most of the reason it's famous is because it was broken. It was broken by a team of British cryptographers at Bletchley Park, led by Alan Turing, who's also credited as being sort of the father of computing. So quite an important person in a sort of field. For the most part, the breakthroughs were made by the team weren't actually due to weaknesses in how Enigma itself worked, but rather in operational errors made by the German operators. Examples of these errors include choosing bad keys, such as AAA, quite easy to break, you just have a bit of a guess, or having a predictable message structure. One of the key things that all the German army units used to do is, first thing every morning, they'd send a weather report through to high command, the German word wetter. This allowed the English code breakers to sort of guess that the word weather would be somewhere in the first few words of the message, and they could sort of use that to sort of help them work out if they could decrypt the message. And once they'd broken a message, because the Germans were reusing the keys for the whole day, they'd be able to read everything that the Germans were sending back and forth between them and high command for the whole day. And they could usually sort of break this on their machines by about 10 in the morning from that first transmission and read everything from there on in. This highlights another key property of good cryptography. Even if the underlying cipher is good, if you make really poor usage of it, a bad implementation can compromise the security of that cipher. Okay, so that was a pretty quick look at a few of the ciphers which have been used in the past. While they're obviously not useful for protecting data anymore, they can help us understand what is required from a strong cipher. We're going to look at some of the more modern ciphers now. And as I was sort of saying in the introduction, modern cryptography can be broken down into several problems that we need different solutions for. The first is confidentiality. We need to ensure that other people than the intended recipients can't read our messages. Okay? AES is currently the sort of the recommended algorithm. It's the one that was chosen by a competition for designing a new cipher. Although there's hundreds of different ones which are also in use for various different purposes and have sort of special properties and reasons for using. There's two main classes of these symmetric algorithms. There's stream ciphers, which work on continuous streams of data. And there's block ciphers, like AES, which break the messages up into separate blocks and encrypt each block separately. We'll take a detailed look at both of those in a few minutes. Another thing that we need to be able to do is key exchange. Even the best algorithms we have for preserving message confidentiality are symmetrical, which means you use the same key to encrypt the message and decrypt it. That means if I want to encrypt a message to you, you need to have the key, and I need to have the key. We need a way of communicating that key between us. With the key exchange algorithms, we have a different set of keys where I have a private one and you have a public one, and that one you can broadcast to the world. I can use that to encrypt messages, but not to decrypt them. Another problem we need to solve is identity. If I send you a message, how do you know it came from me? Well, one way I could do that is to sign it with my private key. Only I have my private key, so if you can verify my signature using the public key that I've published, you know that it came from me. That's a message signature. Authentication. Another important thing is that we don't want messages to be tampered with. I mean, think if someone was tampering with web requests to a website that you're using, they could inject malicious JavaScript into the page, for example. So you want to make sure that that page not only has, you don't want to give away what you're looking at, but also that it hasn't been tampered with. We tend to use cryptographic hash functions for this purpose, and a signature to sort of sign that hash. Another problem that possibly gets overlooked in modern-day cryptography is random number generation. A large number of secure protocols rely on being able to generate truly random numbers. If you've got an attacker that can predict the random key that you've just selected to encrypt a message with, that's not very much good because they can just predict that key and use it to decrypt the message. So random numbers are really quite important in modern-day cryptography. So first of all, we'll take a look at the symmetric algorithms. They're the ones for mainly preserving message confidentiality. As I previously mentioned, we've got two classes of algorithm here, the stream cipher and the block cipher. The stream cipher works by looking at a continuous stream of data. And in order to do that, the stream ciphers act as a sort of a pseudo-random number generator, which is seeded by the secret key. They produce this continuous stream of random numbers, and to encrypt a message, you simply XOR your message with the stream of random data. Your recipient can reconstruct that same stream of random data, XOR it with the ciphertext, and that returns them the plain text message. It's actually fairly similar to how Enigma works, so it's sort of evolved from the Enigma cipher. There's several stream ciphers that we currently use today. Probably the most well-known is RC4, which is used for WEP and some legacy SSL connections. But I've chosen to have a look at a different algorithm today, which is called A5/1. You've probably not heard of this, but I can guarantee that every single one of you has a device on you today that is using this, because it's used to protect voice and SMS messages when you're sending them on your phones. Unfortunately, it has actually now been broken, so it's not really considered secure. There's a lot of research that went into it, and it was broken. But let's have a look at how it works. So this is a diagram of sort of the internal state of the A5/1 algorithm. It consists of 3 registers, one at the top here that's got 19 bits in it, another one which is 22 bits, and the final one is 23 bits. For each bit of the plain text that we want to encrypt, we need to sort of use this internal state to produce an output bit here to XOR with it. And the way we do that is we left shift each one of these registers and XOR all the bits together. The state of the registers is then updated by sort of taking the bit that was there and there, XORing them together, and sticking it back on the end. Take a closer look at how that actually works. So this is a sort of a zoom in on that top register. When you sort of clock it to take a bit off the end, you take that same bit, and it goes through this sort of feedback loop to produce the bit at the end. And you can sort of see this is a couple of iterations of clocking that register around and how it produces the bit back on the end. And then that's sort of then used further on, later on down the cipher. So one of the key things when using stream ciphers that you need to be aware of is because it's the output is combined with the message using XOR, it's quite, and it will produce the same output sequence from the same key. It's vital that you do not reuse your keys when you're using a stream cipher. A lot of the modern ones include a nonce, so you can use the same key, and then you use like a random nonce as a sort of an additional part of your key. But if an attacker were to be able to intercept two messages that were intercepted using the same key, they'll be able to sort of XOR the two messages together and recover a part of the stream cipher output, which they can then use to decrypt your messages. WP is actually vulnerable because although it uses a nonce, an initialization vector, to prevent key reuse, it only uses a really short one, which means that if you sit there scanning someone's Wi-Fi network for long enough, you can wait until they reuse the same nonce with the same key, and you can then use that to sort of start decrypting their Wi-Fi messages and get onto their Wi-Fi network. That's why you should upgrade to WPA. Another thing is if an attacker can guess a part of the message that's being sent, they'll be able to modify it. If you think about a web page, it's probably going to have like a head and maybe some JavaScript. You could probably even access the website yourself and get the exact sort of header that's going to go into that message. You can then XOR that message with some replacement message. This will allow you to sort of change what's in the stream cipher and what's being sent on to the client without them being able to notice. This makes it really important to use a method to verify the integrity of the transmitted message once it's received at the other end. It's not so much of a security concern, but more of a practical one. Most stream ciphers require you to run them all the way through to decrypt a message, and you can't arbitrarily seek into the stream without calculating every output bit that went before it. If you're using it for, say, an SSL connection, an SSH connection or something like that, that's not really massively important. But if you're using a stream cipher to encrypt a 40 gig database backup, and you want to restore a table that begins with the letter Z at the end of the backup, you're going to be there for quite a while generating 40 gigabytes of output bits from your stream cipher. So that's sort of a practical sort of concern that you might need to think about. Moving now on to the block ciphers. The key difference from a block cipher to a stream cipher is that whereas a stream cipher produces a stream of output bits, a block cipher tends to work directly on a piece of your message and sort of like scrambles it and messes around with it and produces a ciphertext from that message. It works on a block at a time, so you generally have to split your message up into separate blocks and encrypt each one separately, hence the name. We're going to have a quick look at how AES works, because that's obviously the most popular and most commonly used block cipher at the moment. It was the result of a cryptography competition to find a new algorithm to replace the DES algorithm, as several key weaknesses have been found in that algorithm. And it was eventually won by a slight variant of the Rheingel algorithm. If you're using the very old, which you shouldn't be doing, mcrypt extension, there is a bit of a, if you use the Rheingel 256 thing, that's not actually AES, it's a different algorithm entirely. So be careful if you're still using mcrypt that you pick the right algorithm after that. So AES works, like most block ciphers, by iteratively applying itself many times over and over to the message. Each time it applies itself, AES has 4 key steps in its algorithm. The first one is a substitution step. Then it does a shift step on the rows of a block. And then it does a mixing operation on each of the columns in the block. And finally, it adds a part of your key to the message using XOR. It then goes back to the beginning and does this again. Depending on the length of your key, it does this a different amount of times depending on the length, so that it uses up all of your key. A closer look, the substitution step. We arrange our message that we want to encrypt in a 4x4 matrix of bytes. So each one of these is 1 byte. So it works on 16 bytes at once. And then we substitute it with another key. This is like a substitution cipher. However, this substitution table is fixed for the cipher. It's always the same for everything, and it's been chosen specifically to guard against a few different weaknesses that were originally found in the cipher. So obviously you can't consider that to be part of your key. The next step is each byte in the row is just moved one to the left. So you sort of rotate the whole 4 bytes round to get the next sort of output stage. The next step is to sort of look at the columns of data instead of the rows, and they're sort of multiplied by a fixed amount to produce a new column of bytes. For the final round of the cipher, this step actually gets skipped. And then the final thing is to take part of your key and XOR it with the block of text, and then you finally get your sort of output block. Obviously, when a block cipher is used on a message, which is longer than the block size, the message has to get split up into blocks. There's many ways in which these blocks and output blocks can actually be used for encryption. Each one of these modes of operation has different properties, but if you use a bad mode, even with AES, arguably the best cryptographic algorithm we've come up with as a species so far, it can be quite insecure still. Some of the modes of operation can even be used to turn a block cipher into a stream cipher. There's lots of possible ones. This is just so I'm going to go over a selection of the most common ones. The first being electronic cookbook, or ECB mode. It's kind of naive in the way that you basically just take the first block of your plain text, you encrypt it. You take the next block of your plain text, you encrypt it and append it to the last one, and keep on going. It's sort of like the most obvious one that you'd think to use, but it's a really, really bad mode. Although a block cipher will produce a random output per block, it's a really random, any block which contains the same original data will come out the same from this block cipher. So a famous example of this is called the ECB penguin. And you can see on the left here we've got a nice picture of our friend Tux. And this is Tux after being passed through a block cipher in ECB mode, which kind of highlights why you should not really use AES because you can in ECB mode, because obviously underlying patterns in the data can still sort of show through in the encrypted version. The next mode is cipher block chaining. This was the sort of the first attempt that we made to fix the problems that the ECB mode have. How that sort of works is CBC feeds the first block of ciphertext back into the next block of plaintext, and it XORs it with the first block of plaintext before passing it through the block cipher. This means that even if you've got the same block to start with, provided the block before that was different, you'll end up with a different block coming out of it. Okay? Similar to a stream cipher, CBC also needs an initialization vector, which is used as the sort of the randomization for the first block that you encrypt. It suffers a similar sort of fall down from a stream cipher in the fact that you have to decrypt the whole message in one go in order to use it. The next mode is actually counter mode. It's quite cool in that it actually turns a block cipher into a stream cipher. How it works is as such. You have a sort of initialization vector or nonce which you pass in, and you also have a counter. Starts at 0, and you just increment that by 1, 2, 3 for each block that you've got to encrypt. And instead of encrypting your plain text, you encrypt that bit of data with the counter. You then XOR that with the plain text to produce your ciphertext at the bottom here. Due to the random nature of the block cipher's output, this effectively gives us a stream cipher, with the advantage that we can actually seek into that stream. And we can say, well, I don't care about blocks 1 through 40. I will just compute the random bit of data that I need to decrypt blocks 41 through 50, because that's the bit of data I want. Of course, because it is effectively a stream cipher, the same precautions do need to be taken when using it, such as authenticating messages and so forth, not reusing keys. The final mode I'm going to sort of look at is glorious counter mode, which is a bit of an improvement over CTR mode, as it adds the authentication part of your cipher into the actual cipher level. How this sort of works is you have a counter, which you increment for each block, but you also have an additional bit of authentication data, which is sort of an additional bit of your key, which you also feed into a glorious function, and then that gets XORed to produce an output block, which authenticates your data. And then when you've finished encrypting it, you get a sort of a you get your ciphertext, and then you append an authentication tag, which your receiver can verify to make sure the message hasn't been tampered with. So far, we've looked only at ciphers for that use a single key for encryption and decryption, symmetric ciphers. This leads to a really hard to solve problem, key distribution. In World War II, for example, the Germans, in order to distribute their keys, sent around big paper books of all the keys they were going to use for the next few months. That meant that, as happened a few times when the English Air Force attacked one of the submarines, they managed to get aboard and steal a few of these code books, and then they had all the keys for the submarine's communication for the next few months. So this is where these asymmetric ciphers come in. Asymmetric ciphers use a different key for encrypting as they do for decrypting. If you think about a padlock, okay? If I've got a padlock, I can pass that to you. You can use that to lock a box, okay? You can then pass that box back to me, but if you pass that through other people, they can't use that padlock. They can't undo that padlock without the key that I keep with me. But I can pass that padlock around perfectly fine, and you'll be able to use that to sort of lock a message. That's kind of the same sort of idea as you have with public key cryptography. One of the most common, well-known algorithms is RSA. What it uses is sort of a modular multiplication as a way of producing a key to encrypt a message. And it works on the fact that reversing modular multiplication is really difficult, but if you happen to know some sort of secret information about how it was done in the first place, that makes it much easier for you to reverse. How this sort of works is you find three large integers, prime numbers, E, D, and N, and then you take your message and you raise it to the power of E. Like this. And that produces your ciphertext when you take it modulo N. Now, in order to decrypt it, you raise that ciphertext to the power D, modulo N, and that produces your message again. However, if you're just left with the constant E and the modulo N, it is really, really difficult to calculate this other value, D. It's like a computationally NP hard problem. So it would take a lot more effort to calculate it. But if you happen to be holding this D, then you can reverse that calculation really easily. And that's where you get your public key, which is the E and the N values. And the D becomes your private key that you keep secret. So you can reverse this operation. So obviously, that solves the key exchange. What about identity validation? Well, turns out we can use exactly the same algorithm, but the opposite way around. I can raise a message to the power of D, which is my private key that I'm keeping secret, and I can publicize that to the world along with my public key, E and N. And anyone else in the world can raise that signature, S, to the power of that public key that I've published, and they can verify that message does actually produce what I say it will produce. And that way you can verify that me, holding that private key, was the one who signed that message. In practice, both of these algorithms can only be used on very small messages. So what you'll tend to find is that you'll take a key for a symmetric cipher, you'll encrypt that with your asymmetric cipher, and you use the symmetric cipher to encrypt your message, and just use RSA to encrypt the key that you're using for your symmetric cipher. The same you can do with your signature. You take a hash of your plain text message, and then you can sign that message with your private key. So, I've only got a few minutes left. So I've covered a selection of the algorithms that are in use today. But what about the practical side of cryptography? How should you go about implementing it in your own applications? Well, first piece of advice is don't. Okay? I hope this sort of talk's given you a bit of an insight into quite how much work has gone into designing these algorithms. But it's even possible, even if you have a secure algorithm that you know what it is, even if you implement that yourself in PHP, for example, you're going to introduce potential vulnerabilities into that through various side channels, such as how long it takes your code to execute, or what memory locations it's accessing on the PC, and all the sort of like the verified versions, the ones you can install, have sort of been vigorously tested against these kind of side channel attacks. So what you should really be looking for is to use existing implementations of these algorithms, ones that have been battle-hardened and tested by people who do this thing all day, every day. For example, most Linux distributions will now allow you to just encrypt a hard drive. If that's good enough for what you need, use that. Okay, that's been well tested, well used by lots of people. Again, all the major web servers support TLS. Use that for encrypted communications. Don't try doing some weird JavaScript AES implementation. That's a really bad idea. Another option, if you're wanting to transfer data between sort of sites on your network securely, use SSH, use VPNs. Okay, all of these things have been well tested and are continually being tested by experts. Most developers aren't cryptography experts, so if you do need to do something a bit more specialized, bring in an expert to help you, okay? If security really matters to you, you need to get someone who has that expertise to sort of produce that, to sort of look over what you've done and make sure that there aren't any glaring holes. It may seem quite expensive, but it's far less expensive than the reputational risk if you do something and it's not right. That said, if you do need to sort of encrypt some of your customers' data, there are ways you can go about doing this in PHP quite easily. There's a lot of libraries out there, but there's only a few that I'd sort of recommend looking at and using. The first is Halite. It's a PHP-based wrapper for libsodium, which focuses on using algorithms and making choices that are secure by default, and giving very few choices to you as a developer. So if you use Halite to encrypt something, somebody else has already made the decisions for you as to what is secure, and that way you can just use it without worrying that you've maybe picked the wrong block cipher chaining mode or something like that. Okay, the author of the Halite library has also ported most of libsodium's functions into pure PHP. So if you're in an environment where, for some reason, you can't install libsodium, or you can't upgrade to PHP 7.2, which includes it as default, you can install the PHP-only version in order to benefit from most of the functionality that libsodium gives you. You might be wondering why I make this recommendation. This is an example of how you would encrypt some data using a symmetric key using Halite. There's very, very little you can sort of get wrong there. You load an encryption key and you call encrypt on your super secret data. And that's basically all there is to it. It's what, 12, 13 lines of code? And that makes sure that you get everything right every time. Okay. Another library, if you're unable to use libsodium for some reason, is diffuse PHP. Its features are a lot more limited. It's got a similar API to Halite, so you've just got sort of encrypt and decrypt functions. But it's a lot more limited. But that's also quite well secured if you need to use sort of AES and things like that. Okay, so nearly done. So if anyone's interested in finding out some more, there's a few bits of further reading here. The first thing I'd recommend is, if you're interested in the historic ciphers and a bit more of the history behind that, a guy called Simon Singh wrote a book called The Codebook. which is quite a good resource on a few of these ciphers. He's got some interesting case studies on what happens when they go wrong as well. He's also got a sort of black chamber website, which allows you to play around with some of these historic ciphers and play with decrypting them yourself and things like that. If you're more interested in the modern side of cryptography, Bruce Schneier's, a leading cryptographer, his website features some do-it-yourself learning cryptography courses where you can learn to sort of design some of these algorithms. Remember his law that anyone can design an encryption algorithm that they themselves can't break, but in order to trust someone's algorithm, they need to have a demonstrated history of being able to break their own ciphers. And finally, that's a link to a PHP crypt that contains a lot of the ciphers that I've looked at today implemented in pure PHP. So if you want to have a look at them in code rather than in diagrams, that's a link for you. OK, I hope everyone's sort of found this interesting. Thank you very much. There's a joined-in link there if you'd like to rate it. And thank you very much. And I'll put that link up for the cipher challenge if you want to have a go at cracking that yourself as well.
Is there any questions? On n'a pas beaucoup de temps, donc on va en prendre une ou deux.
Thank you. If we have several tools to encrypt in PHP, you set some library, but most of the time they ask us to choose some algorithm to crypt the data, or as a normal developer, we can choose the correct algorithm because it evolves all the time, and it's hard to follow it because it's a very complex stuff. And honestly, for me, it's very hard to see that if I encrypt with a correct library, because all experts say it's a good PHP library to encrypt, I don't know if the algorithm that I will choose is the good one. So how can I follow it and choose it?
So the idea of Halite is the fact that it actually makes all those decisions for you. Someone who is actually well-versed in what algorithms and what parameters to these algorithms are secure has sort of made those choices, and he will obviously keep updating those. So if there's weaknesses found in something that he's using, he will update the latest recommended standard. And that allows you as a developer to sort of use that library with fair confidence that the choices that have been made are secure and are going to keep your data safe. Does that answer your question? We can have a chat later if you want to have a bit more of a chat.
It's more, I don't know, the cryptography evolves all the time, and it's just doing the stuff correctly when you don't specially follow what's happening there, and choosing something good to avoid data leak and some other stuff.
Yeah, well, that's why it's a good idea to pick a library that is well maintained by someone who can sort of follow the changes and things like that and keep up to date with those.
Merci à tous. On est un peu short, du coup, on va s'arrêter là, je pense.